Hello, everybody. Welcome to the second installment of applications of the classification of C-star algebras. Bhishan, the floor is yours. Take it away.
Thanks. So in the first half of this mini course, 2 weeks ago, I gave some background about the classification program of C-star algebras. And this week, I'm going to show you how to apply some of that theory to 3 applications. So today, I want to talk about what I will call the Weil problem. Tell you what I mean by this. So to motivate what the problem is, let me tell you about a consequence of the spectral theorem for matrices that you'll all be aware of. So the consequence is this: if we have 2 normal matrices, so 2 matrices that commute to the adjoints, then we can decide whether or not they are unitary equivalent just by looking at their eigenvalues. So for normal matrices A and B, and my matrices we have A. So, unitary equivalence would be A equals U B U star for some unitary U. If and only if, let's say, let's write it like this: sigma A equals sigma B. The spectra of A and B, the sets of eigenvalues viewed as multisets. So counting on this. Right, and then this is just because we should diagonalize these matrices. All right, in fact, something much more than this is true, so much finer result is true. So I'll call this Weil theorem. Okay, right, the 10 million Weil theorems to tell you about one particular one, 1912. So a couple of weeks ago in bed level, Nigel Hickson gave a fantastic talk, which I guess is recorded online, and I highly recommend, on Weil's character formula, another result, Weil, from around the same time. So I'm going to tell you about something else.
Sorry, Bhishan, just a stupid question. Can you remind me what the multiset is?
I just mean by this, you take into consideration the multiplicities of each eigenvalue.
Okay, so take into consideration multiplicities as well. Okay.
Yeah, that's all I mean. All right, so the theorem is that not only can you detect whether or not they're unitary equivalent, it's not just a binary result, you can measure the distance between their unitary orbits by computing the distance between the eigenvalues. So if in the case that A and B are not just arbitrary normal, but in fact sub-arbitrary. So if A and B and matrices are sub-arbitrary, then distance I'll write it as the U AB, and by this I mean the int over the set of n by n unitary matrices of the norm between A and UBU star. Okay, so this unitary distance is measuring the distance between the unitary orbits of A and B, and this is equal to the distance between the eigenvalues suitably injected. So this and the distance is equal to the maximum of let's say I between 1 and n of alpha I minus beta I. So where let's say in increasing order, alpha i's are the eigenvalues of A, and the betas are the corresponding ones for B. Okay, so this is what I mean by the distance between the eigenvalues suitably interpreted, right? But in particular, the unitary distance is 0, meaning the unitarily equivalent precisely when the sets of eigenvalues are the same. All right. So in fact, this particular distance here is measuring what I will call the optimal matching distance between these eigenvalues. So in fact, in this case, this distance, this maximum, is the n over all permutations of alpha I minus sigma I. So that means this distance is measuring all possible ways of rearranging the eigenvalues of A and B and then matching them up together and computing the distance pairwise between these. And I'm saying that this is optimized when we just list them in increasing order. So this I will call delta AB, and I'll refer to it as the optimal mapping distance. Right, so Weyl's theorem is that D with AB is delta AB for self-adjoint matrices. Right, so these two distances are exactly equal. Right, so by the Weyl problem of matrices, what I mean by that is okay, so I mean what these distances, I said this equality holds for self-adjoint matrices A and B. So this just repeats, this is the distance between the unitary orbits, and this is the optimal matching distance between the eigenvalues. But both of these distances make sense for arbitrary normal matrices. So we could still ask the question, is this true, not just for self-adjoint matrices, but for arbitrarily normal elements? So this Weyl problem of matrices is to let me do it like this: identify classes of normal matrices for which we have this equality.
Sorry, I have a question.
Yeah.
Should it be infimum over all statements and map?
You're absolutely right. Yes, thank you very much. Yes. Sorry, yes, absolutely.
And on the left-hand side, there should be some distance between spectra.
So just to repeat, these are the spectra. So the alphas are the eigenvalues of A and the betas are the eigenvalues of B, listed in increasing order. Yeah, but thank you. That's excellent. So this should have been. Can I, in fact, if I do this, can I move you now? Because that's not right. That requires definitely work. Oh, in fact, okay, let's write this. Mass, thank you very much. 1 plus y plus n alpha I minus. Okay, right. So identify classes for which we still have this. I mean, or indeed, maybe it could be true for all normal matrices. So I'll tell you some things that are known. So Theorem This is due to Latvia Davis sometime in the 80s, so considerable amount of time after the biosphere. It holds for unitary matrices. Du equals delta for unitary matrices. And okay, the tricky thing about passing from self-adjoints to other classes of normal matrices is that in the self-adjoint case, when eigenvalues on the real line, there's a natural choice for the ordering of these things. In general, that's not the case, but for the unitary matrices where the eigenvalues live on the circle, in fact, what's true is you can find there exists an anti-clockwise ordering of one and a corresponding anti-clockwise one of the other that matches them up together often. So that sort of goes into proving this equality for unitary matrices. But it's also known that it's not true in general. There are files. Okay, so this is due to Holbrook in the 90s, early 90s.
The previous theorem was approximately which year?
Mid-80s.
Mid-80s. Okay.
Something in the 80s. So du is not equal to delta for general normal matrices.
And we are all the time talking just finite matrices, right?
At the moment, yes, just things. So in this case, there exists a counterexample in the 3x3 matrices. But this proof is not at all illuminating. I think it's some sort of a computer-generated thing. There is an example, why this particular example, I don't know if it's particularly clear. But nonetheless, it's not true in general. Maybe I should mention is you don't have equality in general, but they are Lipschitz equivalent. There is a universal constancy. But by universal, I mean it doesn't depend on n. Constant c, such that delta and du are c Lipschitz equivalent. You know what I mean? We can bound one by t times the other up to this universal constancy. Right? It's something that's a little bit bigger than one. All right. So the question, so this is all about, as was mentioned, just things that are happening in the matrices. But now I would like to ask, can we postulate some version of Weil's problem in the setting of classifiable C-star algebra? So this Weil's theorem for self-adjoints or unitaries or whatever class it might hold for. So does this hold, some version of it, which we'll discuss, holds in this classifiable category in the
You seem to go that question.
let me just remind you, when I say the classifiable category, I mean so E, it's the category whose objects are infinite dimensional. Simple, separable, unital, finite infinite dimension, satisfying uses. And just to remind you that this finite nuclear dimension is equivalent, we could say, nuclear plus, let's say, that was this Jiangsu algebra that it's the unique object in this category that has the same Elliott invariant, so the same K-theory and the same tracial data as the complex numbers, which is why I need to stick infinite dimensional here. Otherwise, the calculation happens. So, and that table means that if I enter by this Jiangsu algebra, I have an isomorphic. And it's a nuclear C-star algebra, so it's the minimal or whatever tensor product.
Sorry, just a naive question, if I may. I'm thinking about an example of a nuclear C-star algebra which has infinite nuclear dimensions. So if I just take simply a topological manifold with an infinite covering dimension, would it do the job?
Yes, that's right, yes.
And would it be Z-stable or not?
No, it would
of course
not be Z-stable.
Yeah, okay, thank you.
Yeah, I mean, for example, because it's commutative, so this would not be. But if you want a simple C-star algebra with infinite nuclear dimension, you take one of these example CTS Paviliton, which is it's an inductive limit of homogeneous algebras, so functions from I think he takes cubes or spheres. You have very high dimensional spheres, so functions from spheres into matrices, and and you build an inductive limit like this. But the point is, what he does is he makes the dimension of these base spaces grow very, 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 very fast. And this it's fast enough to exhibit perforation in K-theory. That prevents it from being Z-stable.
Sorry, but I'm still confused. This is really the logical equivalence? Because by exactly what you told me, take a commutative C-star algebra which has finite nuclear dimension, I don't see how it is Z-stable.
Yeah, what I mean is equivalent in the presence of the other.
Oops, sorry.
Oh, it's equivalent in the presence of the other hypotheses. That's what I mean. So in particular, assuming simplicity. But I guess we probably don't need the UCT for this. But yes, so a C-star algebra that's infinite dimensional, simple, separable, unital. In fact, we don't even need unital. Finite nuclear dimension is equivalent to nuclearity. Okay, and then the key fact is that objects in E are classified by the Elliott invariant. This Elliott invariant, very roughly, is comprised of K-theory traces. We discussed in the first time. So this is the setting in which I want to pose some version of Weyl's problem. I will just say that we will address the question is, in this category, do we have some version of Weyl's theorem? So do we have du equals delta for normal elements in such C-star algebras or some suitable notions? First of all, I'm only going to remember there's a dichotomy that holds in this category. These objects in here are either purely infinite, a very sort of strong notion of infiniteness. Infiniteness is something describing behavior of projections. The other extreme, so things like the Kunz algebras are purely infinite C-star algebras. Graph C-star algebras, whenever they are strongly connected, the graph is strongly connected, is purely infinite. On the flip side of this, we have the stably finite ones. Equivalently, the stably finite objects are just the ones with traces, the ones for which the simplex of tracial states is non-empty. So, and I will only address the question in that side of things. So we will assume, so we will only consider stably finite. Objects in E. And then as I said, it's just that the trait space, basically trading space is non-empty.
Can you remind us again what UCT is?
Yes. The UCT is the universal coefficient theorem for K-theory. It is the simplest way to describe it is that C-star algebra is of UCT class if its KK equivalent to a commutative C-star algebra.
Yeah, I mean, so equivalently, there is this notion of this. Let's say if we're assuming C-star is nuclear, there's this notion of the bootstrap class due to Rosenberg and Schoppert, which is it says that the complex numbers are in this class. It's closed under KK equivalents, so commutative things are in this class. It's closed under things like inductive limits and extensions, and from this you can deduce it's also closed under tensor products and cross products by the integers and the real numbers.
When you said it's equivalent to a billion one, commutative one, what kind of equivalence did you mention?
KK equivalence.
KK equivalence.
So it's a statement about Kasparov's bivariant K theory. So yeah, I mean, you would like to think about KK as there's some relationship between this and homomorphisms between K theory. The UCT said that it's not like of them. I mean, there is a kernel, and the kernel is the X group of these K groups. UCT means we have this kind of short exact sequence. So UCT for A means this holds for A and every B. All right. Okay.
Sorry, Bhishan, just a naive question, but I think it goes into the spirit of what Adam is asking. If I have two C-star algebras that are KK equivalent, this implies that they have the same K homology groups and K theory groups, but not the other way around. Am I right?
Yeah, exactly right. But yeah, that's true. And under the UCT, they are the same statement under the UCT.
Adam, are you happy with this special case?
I'm happy. I mean, I presume we're not going to go into KK.
No, definitely not. Definitely not. I mean, yeah, definitely not. I mean, this week it'll be a sort of background assumption, but I'm not going to go into the nitty-gritty. All right, so I'm only going to talk about static-minded C-star algebras. I'm just going to mention that for purely infinite algebras, there is some work by Paul Kopranis. So I will describe what exactly I mean by the Weyl problem and what exactly I mean by this delta there. In the case of purely infinite C-star algebras, this delta, this spectral distance, is just going to be the Hausdorff distance between the spectra. So that's the right thing to look at. We'll look at something else in our segment. And in fact, for Neumann algebras, on which a lot of this work is based, there is some stuff done also in the 80s by Hiai and I think Nakamura is the second. So the work that they did in the von Neumann case, and I think they also considered both finite and infinite von Neumann algebras, motivated a lot of this. That's I will tell you in the C-star set.
In these cases, for purely infinite and for Neumann, the answer is positive or negative?
Positive in some cases. Not okay. For similar reasons as the matrices, I mean, it's not going to hold in general.
Okay.
And what I'm going to tell you is just in certain cases we'll have a positive result, but not every single.
Purely infinite means that there are some classes.
Yeah.
It's positive.
Is there a simple example of an algebra like that satisfying all those assumptions?
All of these assumptions?
Yes.
Yes. As I said, the Kunz algebras would be an example. So if you know about graph C-star algebras, you just take one vertex and n loops. This will be this gives you the Kunz algebra O(n), and this satisfies all of these assumptions. The only thing is those algebras, as I said, they don't have traces. If you want an example of such an algebra that has a trace, probably the simplest way to build these is a UHF algebra. So you take like a car algebra, take an infinite tensor product of the 2x2 matrices. That would be an example that satisfies all of these assumptions, and it has a unique trace.
Sorry, so your traces are states.
Tracial states. Whenever I say trace, whenever I say trace, I would mean a tracial state. Yeah.
So there could be some traces which are not normalizable.
No. Well, only if you allow traces that are very badly behaved, that take the value only 0 and infinity. for example. So these are the only traces you can have in the purely infinite case. So the trace of the zero element, zero, everything else has to have trace infinity.
So by traces, I mean linear functionals.
If you okay,
few commutators.
Yeah, okay. Maybe what I said is true if you further demand the trace to be lower semi-continuous, which is typically what we do want. We want at least something like this in this context. About non-lower semi-continuous traces, I'm not so sure. Maybe, yeah, maybe there could be. All right, okay. So this just in the background, remember the Weyl theorem, the Weyl problem that we're looking at is, do we have this equality of du and delta? So this is the distance between the unitary orbits, and this is this kind of spectral distance. But in the case of matrices, I defined this delta as the spectral distance precisely as this optimal matching distance between the eigenvalues. In the case of infinite dimensional C-star algebras, this is not really the right notion to look at. We need some other notion for spectral distance, which we'll work our way towards. So that's the first question. First, how to define delta in this context. In this context, I mean the context would go in this category E. So in something like a UHF algebra. So from now on, right, what I'm going to do is I'm going to fix a space X that'll be the shared spectrum of normal elements in my C-star algebra. So this X will be a spectrum. I'm going to assume that this X is a compact. I'm also going to assume it's connected metric space. The reason I'm going to assume it's connected is to avoid projections in C of X. Because if I have projections, then I'm going to run into K-theory when I'm looking at the unitary orbits. And if I want just a purely spectral computation in terms of measures, as we will see, that's not going to work. I would have to somehow also take K-theory into account. So to bypass this problem, I'm just going to assume connect this as a vector. Okay, so I kind of gave away the game there. So we're going to define this delta in terms of spectral measures. That's what we'll do. So, and the reason I'm okay, X, we might think of this as a spectrum, so it lives in the plane. Then this D would be the Euclidean metric restricted to X. But I'll also tell you about a sort of more general setting where we're no longer even talking about this being a spectrum. It can be just any commutative space. And then we'll talk about the unitary distance between homomorphisms from C of X into the algebra. And in that case, so if we have such a homomorphism, so if phi C of X A is, let's say, an injective and unital star homomorphism. Then every trace in here, it pulls back to a trace on here. And that corresponds by the Rees representation theorem to a measure on here. So every trace on A gives trace I on C of X. Hence, as I said, by the Rees theorem, a Borel probability measure. Let's say mu phi slice on X. Right. Okay. So if I am in the special case where, so if X is lives in the plane with the Euclidean metric, so if this is the spectrum
of some normal element A. I'll write this as mu H of, right? So in this case, if X is the spectrum of A, this phi would just be the Gelfand homomorphism from C of X into the C-star algebra generated, let's say the unit C-star algebra generated by A. And I'll just write, instead of mu phi star 4, I'll write mu A on its own, or mu phi star. All right. Okay. So just to make this a little more concrete, I know I said that X will be a connected space in general, but for the moment, let's pretend we're back in the case of matrices. What is this measure? Let's see. So we're taking the unique trace on the normalized trace on the matrices. I said this pulls back to a measure on the spectrum. What is this measure that gets pulled back? It's just the counting measure. So it's the counting measure on the set of eigenvalues, taking multiplicity into account. So the counting measure on the multi-set of eigenvalues.
By the way, Bhishan, you're doing perfectly well with your whiteboards. In the quarter of the time, you have used the quarter of your whiteboards.
I see. Okay.
Just perfect.
Okay. Good to know. Right. So, example. If A is Mn, tau is unique trace, then this Q for A is the counting measure, normalized counting measure. On the multi-set. Eigenvalues of A. So what I mean is, let's say n is 3 and the eigenvalues of A are 1, 1, 2. Then the measure of 1 is 2. Is that all? The measure of 1 is the measure of 1 would be 2/3, and the measure of 2 will be 1/5. That's what I mean by normalized counting measure on multi-set. Okay, so but in fact, it's more than that is true. So and by an application of Paul-Marge theorem, you know about this result. We can interpret the optimal matching distance between the eigenvalues in terms of a certain distance between these measures. So this optimal matching distance. So remember, this was the
Could you recall this whole theorem? Could you recall this whole theorem?
Right. So I can't remember exactly what the conditions is, but we have some, some set X and we have some set Y, and we want to pair together the members of X and Y. And if so each element in X has some kind of preference for the elements in Y to which they can be paired. And if some combinatorial condition holds, then there exists a matching between X and something that we would like it to be paired with, right? It's not so important exactly for us to recall this. I'll just tell you what the
combinatoric argument.
It's a purely combinatoric. So let me just remind you, this was the max one and all right. So this this is the result that I'm telling you. This needs a little bit of argument in terms of this combinatoric, but I'm telling you it's true. It is the inf of the set of bigger than 0, such that mu A. Did I write mu for A or mu A? It doesn't matter. Mu for A of U is that mu for A of U R. And mu for B
U plus U or A U R for all over U. By UR, I mean just the R neighborhood. So the set of points that are R distant from U, at most R distant. So it's a set of X, set X in the plane. Say so everything in this example lives in the plane. So the set of point X in the plane, such that the distance between X and U is at most R. All right, so this is say this is for a given eigenvalue in a given, let's think of this U in some open ball. I'm pairing together this A with an eigenvalue B that's not too far away, that's far away by some distance R. And the claim I'm asserting to you is that one can check by a suitable combinatorics that this optimal matching distance between these eigenvalues is exactly this distance. So it's the smallest R that I need, such that every given set I need to enlarge by a little bit to bound the measure according to A of U by the measure according to B of this enlarged set, and the other way around. All right. I mean, this seems like maybe a bit of a muchness, but another thing that I'm telling you is that this is what's called the infinity Vassarstein distance between the measures mu tau A and mu tau B.
Let me ask you the following naive question. When you look at the definition of this delta distance, it's manifestly symmetric.
Yes.
When I look on the right-hand side, it is not manifestly symmetric, or am I missing something?
It is, because I included both.
And I'm sorry, yes, of course.
Yeah, so, but in fact, actually, it turns out that for this infinity Vassarstein distance, this is automatic. So I could have defined it asymmetrically. It would turn out that it is automatically symmetric, by the way. But let's, as I've written it, it certainly is symmetric.
Yeah. Okay.
Well, this Vassarstein metric is related to moving airs.
This is exactly where we're going today. Exactly this. Yes. Okay. We're exactly going to optimal transport. Exactly this. So this, as to
of the infinity is the infinity Vassarstein distance. Into measures. It is just some distance between measures that is defined in the way I did in the previous one. A bit of warning is that in general, this gives a topology on measures that is stronger than the weak star topology. There is in fact, a whole family of Vassarstein metrics. There's WP for P between 1 and infinity. The WPs for P smaller than infinity always do provide a metrization of the weak star topology. This in general provides a stronger topology. But what is true is that in our setting, in the setting of measures on a connected space, where, and we'll only be talking about faithful measures. So for faithful measures on a connected compact space, it does in fact give a metrization of the weak star topology. All right, I mean, this is not so crucial, just by the way.
And historically speaking, because there are at least 2 Vassarsteins, this is Simon Vassarstein, your supervisor from Glasgow, right?
No, that's Simon Wasserman.
Wasserman, oh, I'm so sorry. I completely confused, yes.
I don't know who these, I don't know if there's more than one Waterstone, as this means, I don't know. Okay, but the point is that this Vassarstein distance, it makes sense in our context. So that's how we make sense of the file problem. So now let's just say A, B, yeah, one of these things. So a lot of what I'm going to say, it works more generally. I don't need full laundry list of adjectives that I wrote for this category E, but just, I don't want to keep writing various permutations of assumptions. So that's all the time to say for now in E. A and E with a trace
So stably finite.
So now the story is about transporting probability.
Yeah, absolutely. That's exactly where we're going. So we let this and then let A be in A, the normal elements.
I'm sorry, I have to clarify it. In fact, this is Leonid Vassarstein. He's in Penn State. I know him, and he actually is also well known for having a very nice version of Sarswell theorem in case of non-compact manifolds.
I didn't know that. I would have thought that this would have been much more classical. Yeah,
much more classical.
Yeah.
I just Google came up. I mean, Vassarstein metric distance appears immediately when I clicked on Vassarstein, and yes, this is Penn State Vassarstein.
All right. Okay. Fair enough. Okay. So the normal elements with common spectrum X, which remember I'm assuming is it's connected. Sort of, but at the moment not really. Just one of the nice things about connectedness is this metrization of the weak side about, but the main reason is we don't want to talk about K-theory, this computation risk. So with common spectrum X, so X now lives in place. So the final problem in this setting is when can we deduce that du AB is, all this W infinity A. So here, I mean, again, the unitary distance would make sense. I mean, the n over all unitaries of A minus U du star. And there, I mean, so in the matrix case, what I said was this optimal matching distance is just the Vassarstein distance, the infinity Vassarstein distance between these measures corresponding to the trace. In the case of matrices, we only have one trace to contend with. In general, we might have many, so we just take that into account. So I take this primum over all traces in A of the distance between the measure corresponding to that trace for A and the same for B. And so this is the problem in this setting. And as has been suggested, where we're going to head is we're going to view this as an optimal transport problem. We're going to eventually try to do some transport of probability measures on the spectrum and then use classification to turn that into a transport of one element of the other by a unitary. So we will use classification to convert this transport map into a conjugated unitary. That's what we're going to do, basically. All right, so, and I'll tell you a theorem now that when we know this is true for certain cases, for certain kinds of X. So maybe I'll just tell you the theorem straight away. Theorem. Okay, so yeah, again, if A E is stably finite, so it has a trace. But this really, as I said, holds more generally than whatever. So then EU AB equals W infinity AB if the results. So the first is due to myself and Aaron Strong and in Thomas 8 years ago or something. This holds if X is an integral. So I mean, this result we proved. So this is the case of self-adjoint elements, basically. So this is really the okay, I said 0,1 with many of these. This is really the generalization of Weil's original theorem to the context of the stable. And but I'm assuming, as I said, connectedness with no spectral gaps in this. And this result actually holds in quite a bit more generality than, as I said, this laundry list. Anyway, next case, so myself, Karen and Alessandro Vignati, I don't know, 3 years ago, 4 years ago, something.
So this holds if X is locally connected. Okay, I mean, as I say, I'm always assuming it's compact and connected, so I want it to be compact, connected, and locally connected. So this means it is what's called a piano continuum. Just other language for describing the situation. One, which means it's a continuous image of 0, 1.
But your X is all the time a compact metric space, right?
At the moment, it is in fact a compact connected subset of the plane, Euclidean method. So I'm talking about the spectrum of normal elements. Later on,
okay.
I'll remove that from the plane together, altogether. Now it's actually in the plane. So it's English image of 0, 1. Okay, in this setting, we need, so this is a much wider variety of X's, but we need some more restrictions on A. So I want A to be A. So again, I want it to be 5. I want it to also have real rank 0. Real rank 0, remember, it means that every self-adjoint element can be arbitrarily well approximated by an invertible self-adjoint element. So an example would be UHF algebra. So the car algebra, the distance product has real rank 0. Real rank 0, and I want this. I want some conditions on the trace space. So I want the trace simplex to be a power simplex, which means that the boundary, the extremal boundary, is compact. And in fact, I want it also to be finite dimension. Have finite Lebesgue covering dimension. I will show you, I will go through the proof of this for the remainder. Both of them use classification, but in quite different ways. So the second, which we'll get to, is more or less what I described and what was already brought up. It's going to be phrased as an optimal transport problem. We're going to transport on the spectrum, use classification to convert that to transporting in the algebra. In the first case, we're going to do the transport just in the algebra directly using classification. So let me show you the proof of the first one. Proof of 1. And this is why this proof, exactly this, is why I wanted to tell you about this Kuntz semigroup. So let me quickly remind you. So recall that, so the Kuntz semigroup. So it's denoted like this, CUA. All right, it's you look at the positive elements in the stabilization of the algebra, and you look at equivalence classes. It's also important for us to remember what the precise definition of this equivalence relation is. Just bear in mind, it is just a generalization of Murray-von-Neumann equivalence of projections. So it's like the Murray-von-Neumann semigroup of projections, just with positive elements instead. The two key things about this object that I want to remind you of. So recall the Kuntz semigroup of A is isomorphic to. And this is where I'm using the fact that A is in this category, E, this classifiable category. So there is this theorem due to Braun, Pereira, and Toms that tells us that for classified or safe algebras, this C of A decomposes as, first of all, so what you do is you look at elements, equivalence classes in here. If that equivalence class is the class of a projection, so this isomorphism from here to here. So if the positive element is equivalent to a projection, you send it to the actual honest to goodness Murray-von-Neumann semigroup. Or otherwise, if it's not equivalent to a projection, you get, I think, what I denoted like this. So this is the set of pointwise supreme. of continuous affine functions. From the trace space to by affine, I mean functions. This is a compact convex set, so functions that preserve convex combinations. Okay, so as I said, if I take a positive element here, if it is equivalent to a projection, I send it here. Otherwise, I send it here. How do I send it here? Remember, there's this thing that I call a dimension function. So if I take the plot in of a positive element in this semigroup gadget, then I get this function a hat. And this sends a trace to this dimension function next to the D of A. This is the supreme over lambda of the trace of the endpoints of A. This is well defined on Kunz classes. But I mean, this function that sends a trace to this supremum is not continuous in general, it is lower semi-continuous. So that's why I end up in this space of convex supremum, not just affine functions on traces. Okay, all right. Okay.
So I might take this opportunity to ask you, and I apologize if I asked it before, but you know, when you have a graph sister algebra, then you know everything about D of A in terms of its graph. How about the Kunz?
Right. Yeah, that's good. It's a good question. It's a good question. Yeah, I'm not sure is the answer. I can just tell you in special cases. So if we look at in the very special case, we're just talking about simple graph sister algebras. Then of course, dichotomy of purely infinite or AF cases. The AF cases fall under this. So we know what the AF case looks like. It's just this kind of descriptor. The Kunz semigroup looks like this. In the purely infinite case, the Kunz semigroup is fairly degenerate for purely infinite simple sister algebras. It's just the set with two elements, 0 and infinity. Because more or less by definition, in a purely infinite sister algebra, any two non-zero positive elements are Kunz equivalent. That's more or less the definition of what it means to be purely infinite for simple sister algebras. So, okay, that's an answer, at least in the simple case. I mean, generally, when you have ideals, I'm not sure, but maybe what should be mentioned is that the Kunz semigroup does contain the lattice of ideals of any sister algebra. Maybe you need stick separable in there, maybe not. But there is an embedding from the lattice of ideals of sister algebra into the Kunz semigroup. That's why it's often it's unsurprising that it's a useful gadget for classifying non-simple sister algebra.
Yeah.
Ideal information. Okay, anyway, all right. So the thing that I really want to remember, you to remember is this. We have this, we know what it looks like in this case. And the second thing I want you to remember is that we can use the Kunz semigroup to classify homomorphisms. This is what I call Roberts' theorem. So Lionel Roberts told us that CU classifies unital star homomorphisms from continuous functions on the interval to stable rank 1 sister algebras. Okay, so stable rank 1 is a similar notion to real rank 0. You delete self-adjoint. So stable rank 1 means the invariable element dense in the algebra. So what I mean by this is, if you give me a CU morphism from the Kunz semigroup of this guy to the Kunz semigroup of the stable rank 1 sister algebra, then it lifts to an actual star homomorphism between the algebras, uniquely up to approximate unitary equivalence. So it's a existence result and a uniqueness result, this classification. Right, so that's what we're going to use. We're going to use our knowledge of what CU looks like and this classification theorem, and then this will provide us the proof in the case where, so this is, you know, exactly C of X for our X of interest in part 1 of the theorem. Okay, so, all right, how do we do this? So first of all, we let B be a simple
we're going to use Roberts' theorem to build what you might call a tracial model for the Caesar algebra A. So A is just some abstract object in this classifiable category. We're going to build a concrete model for it, at least at the level of the trace space. And then we're going to, by this model that we've constructed, we'll be able to reduce the problem into something we can actually solve. So let V be a simple inductive limit of prime dimension drop algebras that has the same trace space as A. So with yeah.
Can you replace this Roberts theorem? This 0, 1, 2 by something one-dimensional?
Yeah. Yes. So more generally, you can replace this by a one-dimensional non-commutative CW complex.
Oh,
that's with trivial K1, crucially.
Trivial K1.
Trivial K1. So trees, for example, would be okay, but circle not okay for this theorem. And the various kind of permanent results. So it holds, in fact, for not just these NPPW complexes, but finite sum or limit the
contractible one dimension.
I guess, yeah, something like this, yeah. Exactly. All right. Okay, so what's a dimension drop algebra? These are the things that are used to build the Jiangsu algebra. So they are continuous functions from the interval into matrices with some boundary conditions. Okay, but all we need to know about this is that so we know from this that the Kunz semigroup of B. The key thing about these prime dimension drop algebras is that they are projectionless. The only non-trivial projection in the algebra is the identity. So the Mary-Von-Neumann semigroup is just the. Now I cannot remember if I've decided that zeros. Let's just say 0 is enough. So it's the number of numbers. Disjoint union with this, and I'm saying the trace space of B is isomorphic to the trace space of A, but it's isomorphic to this. I know that such a B exists. I mean, this is in Zhang and Su's original paper. Even they prove that any metrizable showcase simplex is realizable as the trace space of such an inductive limit. Okay, but the key thing is this: we know what the Kunz semigroup looks like. So we have a diagram like so. So each maybe let's call this alpha A, alpha B.
Sorry, could you go back for a second to the previous slide?
Yeah. Yeah.
So here you say that this Robert theorem requires the assumption stable, that's stable rank 1, and because previously it had real rank 0, right? In the assumption of the theorem.
Yeah, I had real rank 0. In fact, real rank 0 was only an assumption for part 2 of the theorem.
And you are proving part 1.
Yeah, I'm proving part 1.
Okay, so that's irrelevant. Okay, yeah. Sorry for the mix-up. Yeah.
Sure, but I should say that stable rank 1 is automatic for stably finite algebras in this category. Sensibility implies stable.
Okay, so right.
Okay, that's right. So each of these normal elements A and B, they have spectrum the interval. So by the Gelfand map, we have so let me take a CU here. So but by the Gelfand map, I have the Gelfand map gives me homomorphisms from continuous functions on the interval into the algebra. So if at the level of CU, I have maps from CU of continuous functions on the interval to CU of A, which is isomorphic to whatever the Mary-Von-Neumann semigroup is, disjoint union, this premium of affine functions. But then I have CUP, I have a map. So I know this is natural numbers. Disjoint union, the same thing. So I have a map going up into this.
Right, so this is just the class of the unit, so I just send the class of the units to the class of the unit here, then I extend by making a semi-group morphism. This I just identify like this. So then, and again, what I should point out is that, so just like,
sorry, I lost it.
Yeah.
Why you can identify this say, absorbing part of this?
Sorry, yes, because I showed B specifically so that it had the same trace space as A.
Okay.
That was the whole point. Yeah, so I want this absolutely. Okay. So right. So this has no non-trivial projections, but that's also true for this. I mean, the only non-trivial projection here is the unit. Okay. So the image of this is exactly the image of this is the image of this. Okay, so it just the only non-trivial projection is the unit that gets sent to 1, which also is what 1 gets sent to from B. So this diagram commutes. I can find a map from CU of the interval to CU of B such that this commutes. All right. By Roberts' theorem, I can in fact lift this to a star homomorphism. So Roberts' existence. So let's call this alpha A primed, alpha B primed. So we can lift alpha A primed, alpha B primed to star homomorphisms. C 0, 1 to B. And Roberts, by uniqueness, because I have this commutativity at the level of the Kuhn semigroup.
Sorry, can you remind me what these A and B are?
Normal, so A and B are normal elements in A that have spectrum in the interval, 0. That's how I get these maps. So the Gelfand map gives me a homomorphism from C of 0, 1 into A. Then I've just applied the Kuhn's functor to that Gelfand homomorphism.
Okay, thank you. Yes, I've got it. Yes.
Yeah. So this gives me a map of the level of CU. Because the image of this map is contained in the image of this map there, I take this composed with the inverse to get me this map there. That's how I get this map so that the diagram commutes. Right? But then what I do is I use the existence part of the classification theorem to lift these to actual star homomorphisms. And then by uniqueness part of that theorem, because I have this commutativity at the level of CU, these maps, these lifted star homomorphisms are in fact approximately unitarily equivalent to the ones I started with. In other words, what I have is that I get, so that the conclusion is that there are honest to goodness positive elements A primed, B primed, in B this time, with the unitary distance between A and A prime is 0, and the unitary distance between B and B prime is 0.
In other words, they're approximately unitarily equivalent. That's what I'm saying, right?
So all of this to say is what I've done is I've just replaced the problem happening inside this abstract C-star algebra A. Now it's happening in this concrete C-star algebra B that I understand better. That's the take-home message of all of this. But then I can further reduce, I won't go into the details, it's not so hard. This inductive limit of dimensional algebras, I can reduce from positive elements in the limit to positive elements actually in one of these blocks. So further reduce to A prime, B prime in a dimension drop algebra.
Remember what I'm trying to do is I'm trying to show that du AB equals this Vassarstein distance between A and B. But then I can even reduce further. These are now functions from the interval into matrices. But now I can, honest to goodness, reduce the problem to matrices just by diagonalizing these elements A and B. So reduce to A prime, B prime, actual matrices. But then we're done because we know that du is equal to this spectral distance by Vassarstein theorem. That's a sketch of what's going on, but essentially that's what it is. Okay, so to just summarize this, we use classification to reduce the problem from an abstract C-star algebra into a concrete one. And then we further reduce to algebras of functions from the interval into matrices. And then by diagonalizing, we can even further reduce actually to matrix, a matrix problem, which we know and solve. So that's it. That's how you.
And you use the continuity of this Kunz functor, right?
Yes. Yes. Absolutely. I mean, there is something to be done here about reducing from the limits to the blocks. No. The key idea is as I described. Okay. So that's the proof of one. So
I like that. I have a question.
Yeah.
So this result relies heavily on classification. Are there some examples, simple examples, in which you can see how this transport of probability is transferred into this conjugation by unitaries?
So, okay, maybe this will become clearer in the proof of this second case, which I will describe now. Maybe we'll see this, maybe not, but I think this will come closer to answering the question than this. Okay, so 2 was around, I'm assuming that X is now not the interval, but some piano continuum, potentially. So in fact, what I'll show you is not the proof of that too, but I'll show you the proof of something else, which uses very much related ideas. So to illustrate the proof of 2, so let's consider more general setting. Done by, I mean, non-planar. So X is no longer has to be a subset of the plane. Non-planar setting. So X is just compact metric space. Okay, so this time, so there is no normal element for which this is the spectrum. That need not even make sense. So we need some way now, some new way of making sense of the unitary distance and the spectral distance. What we'll do is we'll use as a reference set, relative to which we'll measure these distances, we'll use Lipschitz functions in this. So we measure distance of let's write it as the one limit, limit on xt. So this is the set of functions from x, let's say real valued functions, such that the distance between f of x and f of y is at most the distance between x and 1 for all x, y, and right. So for this time we had in the planar setting we had canonical maps from X into the algebra, the Galfand maps corresponding to our normal elements. Here we'll just have some maps. So for let's say phi and psi from C of X into some unital star monomorphisms. We define this unitary distance, du phi psi. We'll just define it in terms of relative, as I say, to this Lipschitz function. So we'll define it to be the nth of all unitaries, the supremum of all of these functions, let one of the distance between phi n and u psi n. Stuff. So this is the unitary distance. All right, so okay, in other words, what would it mean to say that the unitary distance between phi and psi is less than epsilon? It means that there is some unitary in A that conjugates all of lip 1x to the image of psi of that lip 1x. Under this single unitary. So I want a single unitary that conjugates the entirety of lip1 xt. All right. this is reasonable because this set of one Lipschitz functions is, right, well, it's not compact, but it's like almost compact in a way. What I mean is, so note, I guess what I'm trying to say is that du phi psi is 0 if and only if phi is approximately unitary equivalent to psi. Remember, this means that for every finite f, for every epsilon bigger than 0, there exists a u such that u phi f minus u I u star less than epsilon for every f and f. Wait, I mean, what I'm trying to say is that lip one, as I said, it's not compact, but it kind of almost is because if I allow for translations, so it's you know, this is my set x. Let's just pick the point x0. What I know is that for any other point x, the distance between f of x and f of x0, f of x minus f of x0, is at most the diameter of x, right? It's at most the distance between x and x0, which is at most of the diameter of x. So in other words, f of x, if I translate f by f of x0, I'm still a Lipschitz function, and now I am bounded in norm. So I can, it's lip 1xt is if I scale my function, if I translate my functions, I land into one Lipschitz function that is bounded in norm. So it intersects the ball of radius, the diameter x of C of x. And this is compact. This is compact, right? By Arzel-Ascoli, if you like. It's equicontinuous because everything is one Lipschitz and it's uniformly bound, right? So modulo R, it's compact. And the point is that for unital star homomorphisms, they will agree on this R part. So I could have, instead of defining it, this supremum over this, thing that's almost not quite compact, I could have just replaced it by the compact part, okay? And it would have been the equivalent distance, right? But a compact set is just as good as a finite set. So that's why that's why I have this equivalent, right? So they are 0 if and only if this unitary, the unitary distance is 0 if and only if they are approximate unitary. So I'm just trying to convince you that this is a reasonable distance to define. Okay, so that is how we define the unitary distance. And as for the other distance, the spectral distance, it makes sense. We just keep that alone. We leave that alone. So we define W infinity of phi just as before, just to be the supremum over all traces of the infinite distance between the measures that these maps go on. Okay, so now the question is, when do we have du between these star homomorphisms? When is it equal to W infinity? So what conditions do I need on what conditions do I need on X, on this commutative space X, this metric space X? What conditions might I need on A to give me this quality?
Sorry, but I completely don't understand this line about leap 1 or leap prime. I don't get it totally.
This line?
Yes.
Okay, what I'm saying is, suppose that f is a Lipschitz function, right? Let's fix a point x0. Okay.
No. Wait, maybe because you see you're pointing on the screen. I don't see what you're pointing on the screen. I mean this one.
Yes, yeah. Oh, I see. So this is yes. This is what I'm addressing. Yes, exactly. Right. Okay. So let's this is my space x here, this blob that I've drawn. Let's fix a point x0, and let's fix a function f that's
this lip one. Because by definition of being one Lipschitz, the distance between f of x for any x in the space and this f of x0 is at most the distance between x and x0.
So that's the definitions of lip1.
That's the definition.
Okay.
And by definition of diameter, this is in other words at most the diameter here. So if I define G to be f, so G is f minus f of x0. Then this function is still in lip1, translating by a scale that doesn't affect this Lipschitz condition. But by this inequality that I've just demonstrated, it's also in its norm. The norm of G is at most the diameter of x. That's how I get this here. So this lip1 minus r, so f minus f of x0 is equal to G, which lives in this intersection. Based on this, I'm taking an f in here, I'm taking f of x0 in here, I'm taking G in here. G is the difference. Okay, so all I'm trying to demonstrate is that lip1 is a set of translations of a compound set. That's the key point.
So this B, it reads how? You have B diameter of x?
This is the ball of radius.
Ball, okay.
Sorry, yes, the ball of radius, the diameter of C of x. So the set of things in C of x that have norm of most diameter of x.
Okay, thank you.
Yeah, and as I said, by Azel, I guess this is okay. All right. So now to address the question, for which x can we expect this to hold? Let's now finally get to this transport. So let me define. Let me say that xd has continuous transport constant. Kx, if the following things. So if for every nice measures, so for every, let's say, faithful and diffuse, or else probability measures. Mu next, and every epsilon equals 0, I can transport one measure onto the other as efficiently as possible, and the measure of efficiency is exactly this infinity Vassarstein distance between the measures. That is the notion of transport problem I'm setting up here. But I only need this up to epsilon. I can allow for some wiggle room. So there exists
what's a generality about x and d, an arbitrary metric space, or?
It's a compact, let's say, path-connected metric space, compact path-connected metric space.
Okay.
There exists a homeomorphism H from X to X. All right, for technical reasons, which we will see maybe if we get to it, I want H to be homotopically trivial. I want it to be homotopic to the identity. Homotopic. Identity X, so set of that. It's first of all, I want, let's say, the infinity distance between H star mu and mu less than epsilon. So here, this is the first forward measure. So mu composed H and beta, like. I want, secondly, I want, well, I guess this is all of it. Yeah, as I said, so I wanted to push mu onto mu as efficiently as possible, measured by double infinity. And this notion of the transport. So in other words, I want the distance between H and the identity map. By this I mean supremum or points, the distance between h of x and x to be at most kx times w infinity u plus some ribbon.
Sorry, in your last but one line,
Yes.
in here, you have h lower star v.
Yeah.
Is equal to v composed with h minus one. So
Yeah.
So now this h minus one, what is this?
I just mean literally.
It's a measure. It's a function on functions.
Yeah. Yes. Yeah. I mean literally this h star
Evaluated on a function, it is
mu of the pre-image.
It's how you define the push forward measure.
on opens.
Yeah.
So you are defining this as so measure. This is a Borel measure.
Yes.
Regarded as a function on sigma algebra generated by opens.
Exactly. Yes.
Okay. It's not on functions. Okay.
Exactly. Yes. Exactly. Okay. So, but all of this is just to say that up to some constant, which maybe captures some of the geometry of the space in a suitable way, I can move mu onto mu by homeomorphism as efficiently as I can. So as efficiently as I can, the extent that the geometry of the space allows. Let me, by the way, this H is often called I'll call it a transport map. So just to relate this to the discussion that we've been having about this continuous transport Mark moving problem, it's something very classical. I guess it goes back to the 1700s. This thing by Monge. We think of this nu as being some massive Earth, and then we have I want to move this massive Earth from some distribution of piles to some distribution of holes, represented by some other distribution mu. I want to do it as efficiently as I can with respect to some cost function here. So the cost function in this setup is this infinity, is captured by this infinity Vassarstein distance. What makes this definition a little bit different to this kind of classical transport problem is I really want this state to be continuous. Often this problem kind of lives in LP. It's often enough to get sort of integrable function transport map. In fact, often, so this framework of wanting a transport map H is what you might call the Monge transportation problem. There's a kind of dual formulation due to Kantorovich, which is about finding an optimal coupling of measures. If you know about this setup. All right, that's not important. All right, just as I said, moving one measure to the other as efficiently as we can, given the geometry of the space X. So just a couple of comments, and then I'll give you some examples of some cases where in fact kx is 1. So note, in general, kx is always going to be bigger than or equal to 1. That's just if you stare at the definitions for a minute or two, this will pop out. But in fact, if x is a compact connected, and okay, because I threw in this condition about wanting to be homotopy to the identity, let's also say contractible topological manifolds. Then it's at least smaller than infinity. So in other words, there does exist at least one transport map from a measure to another. So this is a theorem due to Octobi and Ulam. So the theorem which they proved in the 40s is that in this setup, if I'm on a manifold like this, then whenever I have two measures mu and nu that are faithful, maybe I didn't say, but by faithful I mean that the measure of any non-empty open set is bigger than 0. Diffuse meaning there are no atoms, no points with positive mass. So whenever I have two such measures on a manifold, I can always find a homomorphism that maps one measure onto the other, exactly onto it. So this is the theorem that they proved. So at least in this setting, contractibility gets homotopy conditions. then I'm at least taking the I'm taking a variable or a non-empty set. So I get a language transport complete. Okay, but let me tell you now about some cases where.
So, sorry, when I ask you about this contractibility,
yes,
this contractibility allows you to forget about this homotopy.
Yeah, okay. Yeah, only this. Yeah.
But if you forget about contractibility, what can?
Let's see. Let me give you some examples. So theorem. So due to myself and Karen and Alejandro, and then in a follow-up paper, I generalized some of it. So K of X is 1 if, okay, so first of all, the best case scenario is unsurprisingly if X is an interval. I said 0, 1, but any interval. This is the transport mark that you get is H is F. I always get this from F nu, where F nu here you see it is
Measure.
Yeah.
F of t.
Exactly.
F of t is equal to the measure.
Exactly. So measure of 0. Yeah. Right. So this is the kind of prototypical example of a transport map. It's called the increasing rearrangement map. So you can check that this does push mu onto mu, and it does push it by at most the infinity Vassarstein distance between the measures. In fact, it does it even better than this. It moves it by at most the p Vassarstein distance for any p between one and this. So this is the best case scenario. Secondly,
so this means that these two measures, the distribuant of these two measures are related by h.
Yes, exactly. Yes. Yeah, this is the one that does the transfer. Next, for very similar reasons, in fact, the same reason. So X is a circular arc. Up to a semicircle. Circular arc with the Euclidean metric. So I have this arc living in the plane. So X is subject to the C. And I'm measuring the distance. I'm not taking the geodesic distance, I'm taking the Euclidean distance. Which is why this only will work up to a semicircle. Because if I have some wide circular arc, and I imagine that I have some measure supported at this endpoint and some other measure supported on this endpoint, then the infinity Vassarstein distance between these two measures is very, very small because it's measured well with respect to the Euclidean distance on the plane. But the transport, any homeomorphism of this arc to itself that pushes this measure onto this will be far away from the identity map. Wait, so Kx will be bigger than 1 for circular arcs, bigger than a semicircle with the Euclidean metric. If I took the geodesic metric, it would still be 1.
But why it is 1 is semicircle?
I mean, this needs some proof, but it's essentially because the Euclidean metric is equivalent to the geodesic metric. It's
pi is different from 1.
Pi is different from 1, but it doesn't matter. It doesn't matter.
Okay.
It doesn't matter. The only thing that can go wrong is when the space kind of bends in on itself. As long as this doesn't happen, it doesn't matter. Maybe this needs a little bit of thought and a little bit of checking, but it's true. It's true.
All right. Can you explain these functions? F mu, they are functions from where to where?
So this is a function
interval.
The interval to the interval. Yeah. So this is from 0, 1 to 0, 1. So f mu of 0 is mu of just 0, which is 0, because there are no atoms. So f mu of 0 is 0. F mu of 1 is the measure of the full interval, so it's 1. So it's some
monotone function.
It's a monotone function from 0, 1 to itself. And I mean it's continuous.
And because it's monotone, it's bijective.
Sure. Yeah. But I mean, yeah. So these are indeed homomorphisms.
It's strictly increased because this measure has no atoms.
Well, I guess even if you did have atoms, it would still, it's strictly increasing because of it's faithful, because it's faithful.
Because it's faithful.
Because it's faithful, it's strictly increasing. It's continuous, I guess, because it has no atoms.
Because, yeah.
I guess.
Yes. Yes.
Okay. All right. So circular arcs, as long as they're not too big, but in fact, the full circle is okay. So x equals full circle. It also has, I'm describing situations where kx equals 1. And this is how does this work? If I have two measures on the circle and I want, again, with the geodesic, with the Euclidean metric. Well, if I have two measures on the circle, I can kind of approximate them by actually finitely supported measures. And then there exists a listing of these finitely many points where both of them are anti-clockwise, and this witnesses this of the infinity distance. And then I kind of just match them up together and construct a transport map this way. All right, but I'm just telling you for a full circle, I have kx equals 1. In fact, compact convex subsets of Euclidean space of Rn. Let me just say Euclidean space. I don't know why it has to be Rn. Cn. Why do you? Oh no. Oh. Yeah. Okay. Of Euclidean. And lastly, generalizing this. Oh,
what is it below?
Generalizing this, Riemannian manifolds. So, Riemannian manifolds. Of dimension with annoying big n equals 3 with the intrinsic metric. So the metric can divide the shortest distance between paths. All right, why do I need this dimension bigger than 3? Well, so there's no restriction on dimension for the compact convex of the Euclidean space. How does this work?
They have it's not necessarily in French.
Thank you. Yes, yes, thank you very much. Okay, yeah. How does this work? Again, let's say I have two measures on my manifolds. I approximate these measures by finitely supported ones again, and then I connect these finite sets by JD6 essentially. So in here, I connect them by straight lines. Okay.
So this must be at least path connected.
Yes, absolutely. Yeah, I'm assuming in fact path connected. You are right. Yes. So I connect my points by GD6. These GD6 might intersect, which is a bit of an annoyance. So I perturb them so that they don't intersect. This perturbation works very easily in dimension 3. You can always just lift. I have enough room to just lift one GD6 over the other. But then once I have these GD6 that are nowhere intersecting, I construct little tubular neighborhoods around them, and then I build these homomorphisms just within the tubular neighborhoods and then extend to the identity outside of these things. That's a rough idea of how this works. You don't need this restriction of dimension big into 3 Euclidean space because even if they do intersect, we don't have the extra dimension to perturb them, but we can still kind of build a neighborhood around the point of intersection and kind of move things around suitably to. It's an argument that needs to be proved, but it's true. But when we're not in Euclidean space and might have some genus on the surface, I don't know. I don't know if this is actually true in this case. Like I think it should be fine on the surface of a sphere, for example. I think it should still be true. But on a torus, I'm not sure whether you have kx.
Can you come back to the previous point? No.
Yes.
Compact convex subgroup. How convexity?
Just for the property of connecting by D6. by straight lines. Yeah, that's where convexity comes. I want to know that.
Okay, so you don't have this problem with the excess of this distance because
exactly.
The of this.
Exactly right. Yes, exactly this. Yeah. Okay. So all of this just to say, I'm not just.
Wait. So am I to understand that the 2 torus is not the convex subset of R3?
No, it's not.
Okay.
Because it's the whole. But yeah, so I actually at the moment I'm not sure whether KX is 1 for the torus. Maybe it's not. Yeah, I suspect it's not actually. Anyway. Okay, but whatever. So here are just some variety of examples where I know that KX is actually what. But here's the theorem in this setup. So that this Weil problem. So let's suppose. Okay, so X is this compact path-connected metric space with KX, this transport constant, that's infinity. And I also want the K theory to be finitely generated and torsion-free for technical reasons. And I want, let A be real round 0 plus 5 6 round 0 with this extreme boundary compact. Handwriting is getting out of control. Compact and finite dimensional. Then what I can say is that I have an inequality holding. I have W infinity phi psi is at most the unitary distance phi psi, and that is at most kx times the spectral distance phi psi. So this is for all unital star homomorphisms phi psi. Unital star homomorphisms that have the same K theory. So with.
Sorry, can you remind you what you mean by this kind of boundary of a trace space?
Yeah, so the trace space is a compact convex set.
Yes.
So the boundary is the extremal boundary in that sense. So an extreme point of a convex set is one that cannot be written as a linear combination.
Okay.
So if it's the circle, if it's the disk, the extreme boundary is the boundary circle. It's the square, the extreme boundary is the 4 corners of the square.
Yeah, thanks.
Okay, so, yeah, right. So,
sorry, I forgot. What argument shows that this boundary is a closed subset?
It need not be. Boundary. This it's an assumption. By compact.
Okay.
Yeah.
Okay.
Yeah, it's definitely an assumption. For example, this Paulson simplex where the extreme points are dense in the. So yeah, this is definitely not closed. Yeah, this is definitely a structure. I mean, I'm not as closed, but closed and then finite dimensional.
Sorry, what do you assume about these phi and psi? That these are injective star homomorphisms?
Injective unital star homomorphisms that agree on K theory.
Okay, thanks.
So, right. So, okay, just to repeat.
Could you remind me an example of such A, such that this boundary is compact?
UHF algebra has unique trace.
Okay.
It's just one point. Okay. Or, for example, if I take C of X, right? The trace space is the space of measures on X. The extremal boundary is just the point evaluations. So it's if
space is compact.
If the space is compact. Yeah. So in this case, the extremal boundary is just homomorphic to X. Yes. So it's compact. But in fact, this describes all such examples. So every simplex or compact boundary is of this form. All right, so okay.
Do you have a non-commutative example?
Yeah, sure. I mean, yes, any metrizable showcase simplex can be potential trace space of a classifiable C-star algebra, potentially. I mean, you have to build it. Okay. So, I mean, it's a bit difficult to describe to you what it looks like. You can build it as an inductive limit.
So this is the result of this definition of this classifiable class.
I mean, it's something that is proved about this classifiable class. Yes, there is a theorem that any metrizable showcase simplex can arise. I mean, any compatible possibility for the invariant is possible, is attainable. But I mean, you can. I'll talk about this a little bit more on Wednesday. I'll remind you how to build simplices as projective limits of finite dimensional simplices. This is how you can do it. That's how you can build a C-star algebra with the right trace space. A properly non-commutative, something simple with the right trace space. You take your simplex that it's trying to get, you build it as a projective limit of finite dimensional ones, and then you use that to build an inductive limit of C-star algebras that gives this as the trace space. That's how you would get such an A with these conditions, right? But okay, so just think this real round zero condition, AF algebras would satisfy this. So this all for certain kinds of AF algebras. And X, remember, this is compact, path-connected metric space with this finite. So in particular, notice that here I have this inequality in general. So for example, if X is not a circle, but an ellipse in the plane with the Euclidean metric, then for similar reasons as for this almost but not quite circle, Kx will be bigger than 1 for this. So here I would have, by this result, just really an inequality. But in these situations where I have Kx actually equal to 1, I have equality here. So I've answered the Weil question for these kinds of examples. So in particular, what I can, so an X that has all of these conditions, that has Kx equal to 1, and finitely generated in torsion-free K theory would be certain kinds of Lie groups. So for example, let's call this a corollary. If X is UN or SUN or FPN for an EN or some N, and A is in the A is as in the theorem, and so phi and psi. So these universal star monomorphisms that agree on K theory. So then I have equality. Du phi psi is equal to doubling and phi psi. What by which I mean, okay, I said, what's the metric? I just some metric that some Riemannian metric on these monopoles. I guess for a semi-simple compact.
So if this metric is arbitrary, how can you use this group structure?
The group structure is not really playing a role, only in the sense that the group structure tells me what the K theory looks like. And it's and the K theory is torsion-free and finally generated in these for these particular. That's
it's only about K theory.
It's only about K theory, yeah. But yes, I mean it is a bit, I don't know, tantalizing in a way. I do wonder, it's not something I've managed to pin on, whether, I don't know, you could take a genuine non-commutative compact quantum group, to take some deformation of these and ask a similar question. Look at star monomorphisms from a Q deformation of these guys into these kinds of A's. Do we have something like this? You need to, realize these as metric spaces in the right way. Maybe it's one of these, Riefel's notion of a compact quantum metric space.
What about compact homogeneous spaces like complex projective?
Yes. I think also some homogeneous spaces would certainly fit the bill. Yeah,
compute K theory.
Absolutely, yes.
Some of them
have
non-free.
Exactly. Yes. Exactly. But in some cases, yeah, you do get it. Yeah, you do get absolutely. Okay. All right. Yeah. So yeah, as I said, I do wonder about few definitions, please, but I don't know. Okay. Okay, I have 15 minutes left. So maybe let me try to give you a little bit of the flavor of the proof of this theorem. So this is the theorem. But again, it's going to be, as I said earlier, going to, by definition of this KX, this means that there is some transport map that maps the phi measures onto the psi measures up to some constant k of x. And then I'll just use classification to translate this transport map into a conjugating unitary, actually in the output. So that'll give me a statement about E. Okay, what I need to do this is I don't just need the classification of objects in the category. I need the result that tells me that morphisms into this category E are classifiable. So this is, so this is the classification of morphisms into this classifiable class. This is due to Jose Carrion and his co-authors. So this archive paper that appeared a few weeks ago, Jose Carrion, J.B. Gabe, aren't wishes to White. Also, in some circumstances, it's appeared in work by Carl and Hume. The result, I'll phrase it like this. Right. It's a bit of a mouthful as well. So let B be separable unitary. Just think in what I'm going to say is less about it, because B will be, in particular, it could be C of X. Separable unitary nuclear it's an integral. And let's say A is one of these objects in E. So I'm not assuming B is simple in particular, but A needs to be simple. And finite infinite dimension as well. So then, for every unitary embedding, the way I'm going to write this is not the full generality of what they prove, it's just a simple version of it that I would like to use in this case. But it's not quite as fully general as in this case. So for every unitary embedding, phi B to A, L in B compact. Okay, so just think this is L, this compact subset, and B is this compact core of the lip1 set. And epsilon bigger than 0. There is some delta bigger than 0, such that if I have some other embedding phi primed that is delta close to phi at the level of the invariant, then they are unitarily conjugate up to epsilon on this compact set. That's what the statement will be. So such that if phi prime, so such that given another unitary embedding, so given phi primed unitary embedding B into A, so that we're kind of vaguely phrase it like this, so that agrees with phi on K theory. And delta agrees up to delta on traces. There exists a unitary such that the premium of X and L's of phi F minus phi primes times U phi prime F U star less than X. All right.
Okay, I need some clarifications, please. So
Yeah.
first, what assumptions I'm missing for B? I mean, when compared to this category E of classifiable C-star algebras. So I see that we are missing what? Z-stability, what else?
Importantly, crucially, simplicity as well.
Simplicity, yes, of course. So I'm missing simplicity and Z-stability, right?
Yeah, so you should think for our usage B is C of X. Yeah. I'm just making the point that they prove something much more general than just B equals C of X.
Okay, I've got you. Yes, this is a very good answer. Now, I'm also confused about this script L subset of B. What is it?
You should think of this as lip1, but not lip1, but this compact part of lip1 that gives me all of lip1 via translation. So it is this, whatever it was, this thing here. So you should think of this as this L. Right? It's the thing with respect to which I'm measuring my distance. This is the nice compact set that I'm measuring du and du relative. Okay, so that's what you should think of L.
Okay, and how does it? So this is a compact subset of functions which are somehow leap functions, but how does it figure with L in your theorem?
F belonging to L.
F belongs to L. So I can find this to the
supremum is here. Okay, thank you so much. Yes. Okay.
I find one unitary such that for every F and L, I can conjugate the image of phi, the image of phi.
So for this compactness.
Absolutely, yes. I mean, really, yeah. Usually one would say this for finite sets, but compact is just as good as finite. And I want to use it for compact sets, so that's why I said compact. Okay, so the thing that I've been a bit vague about is agrees with phi on K3 and delta agrees on traces. This, in the current usage, when the A in the theorem that I proved, this A is in fact real rank 0. I'm also assuming that the K theory of X is finally generated in torsion free. In this setting, this very special case, agreeing on K theory literally just means that K star of phi prime is equal to K star of phi as maps from K star of C of X to K star of A. That's all it means. In the more general setting, it's more complicated. That's not enough. You need not just to consider K theory, but you need to consider K theory with coefficients to account for potential torsion. You also need to consider Hausdorff's unitary algebraic K1 to account for rotations happening when we don't have a real rank 0 C-star algebra. So there's a lot more to this theorem than just the naive Elliott invariant K theory plus traces in the general setting. I will talk about that a little bit more Wednesday. So on Wednesday, I will go into this theorem a little bit more detail. I'll tell you what more you need than just the Elliott invariant classification morphisms.
Could you explain delta traces?
Yeah. Okay. So yeah, I mean, so okay, so proof of theorem. Let's just assume that A just has one trace. Just for simplicity. I mean, so in this case, delta gradient on traces, literally, you can interpret it like this. I just literally mean the infinity distance between this measure mu phi star call and
You can restrict this tau to B.
Yeah, so remember in the theorem, B is C of X. B is C of X in this theorem. So I'm just telling you what delta agreement on traces means in this particular usage of the statement. In this case, it just means this distance that multiplied. So the reason I can interpret it like this is because these are faithful measures on a compact connected space. And what I told you was that W infinity provides a metrization of the weak star topology. In general, what it means is you take some metric that gives you the weak star topology, and you want this the distance between the traces that so if you want the supreme of all traces in A of the distance between phi, the pullback of the trace along phi and the pullback of the trace along phi prime to be less than delta. So it means delta agrees means in a metric that gives you the Weak-Star topology on traces on V. That's what it means in general. But in this particular usage of it, we have this nice way to describe that. Literally just means that this W infinity distance is less than delta.
I don't understand this.
Yeah.
Now you have phi and psi.
Okay, yes, I have not.
Before you had
Yes.
phi.
Yes. Because okay.
What is phi here?
So the static of the theorem is I have two homomorphisms, phi and psi, C of x into A. That's the static of the theorem, right?
Yeah, indeed. Yeah.
The reason that I didn't say this phi and psi in this is because I'm not going to apply this, in fact, to
So let me write. So the way you prove this is like this. Okay, so I'll tell you. I'll tell you now. So we let H be a transport map. But that H star nu is mu up within some deltas here. So what I mean is, the W infinity distance. That's in delta, right? So this is mu. Sorry. Yeah. This is mu. Okay. Now I define phi prime to be psi composed with H.
Yeah. I always. Yes.
Phi composed with H star, let's say.
H star.
It's inverse because it's open set.
H star is a map from C of x to C of x.
So now
That's right.
okay. So now it's radon measure.
So yes. Okay. So this is my frame. And the point is that this phi prime now this phi prime, its K theory is the same. This only here is why I wanted H to be homotopic to the identity. Because H star now is the identity on K theory. So the K star of phi prime is the same.
In general, it depends on homotopy class. Okay.
That's exactly, yes. So in general, this is by that assumption, it's the same as K star of phi, and by assumption in the theorem, this is the same as K star of phi. Okay, so this phi primes agrees with phi on K theory, and W infinity of phi primes of phi is less than delta. Because the measure of phi primes is H star mu, and the measure for phi is mu, and by assumption it's at most delta. Okay, so I apply the classification theorem here. I mean, I'm sort of almost out of time. I don't know how much more I can say about this. So I mean, the classification theorem, classification of morphisms. Tells me that du of phi and phi primes is less than epsilon. Right? So okay, maybe I'll just try to what we have is this. So du of phi and psi is at most du of phi prime and psi plus some epsilon. But this is by definition the inf of unitaries, of supremum, of functions in the one, of I need to do phi prime.
Now ellipse one or L?
L is lip one. In my usage of the theorem, L is lip one. I state the theorem generally, but I'm applying it to the special case of B equals C of x and L equals lip one. It doesn't matter. Remember, by the argument I said it's not compact, but it is up to modulo this translation by R.
Okay.
And unital homomorphisms really are compact. So it doesn't matter. That's not compact.
Okay.
I could write
good.
Intersect the ball of diameter, if you like.
Okay.
No, this is
okay.
all right. So this is phi prime of F which is by definition psi of f composed of h minus u sine f u star. This infimum is, in particular, I could just take u to be the identity. So this infimum is smaller than the supremum for f, and let me just write alpha property of psi f composed of h minus psi f. Psi is a unit, it's an injective star homomorphism, so this is in fact just the supremum of f composed of L of f composed of h minus f. But here's where I'm using that these functions are Lipschitz, and here's where I'm assuming that the distance between h and the identity is at most kx times w infinity. So this is at most, okay, I'm all the time together in that section. So this is at most so it's at most kx w infinity phi psi. Like that. Okay. All right. So this is a very rapid display of at least half of the theorem. I proved one inequality. Du is at most kx w infinity. You can continue this chain of inequalities, and this would give me the other inequality. Okay. But just to sum up, I know I'm already a minute over time. I'm just using the fact here that h, the distance between hx and x is at most kx times this infinity distance. And I'm using the fact that f is a one-limited function. Therefore, the distance in the function values is also at most that distance. Correct. So that is how I convey optimal transport in the space into a unitary conjugate, how I relate the two concepts via classification. All right, I stopped. Sorry for going over.
Thank you so much. Any urgent questions? If not, let me stop recording and then we continue on Wednesday. You have a question?
Yes. Assume that we have an algebra of 2 by 2 matrices.
Yes.
Okay. And I want to know what is the space of unitary equivalence classes of normal elements of this algebra. Is it something obvious?
You're right. I mean,
because the distance is the difference in this on this space.
Yeah, I guess it's multi-steps of pairs of complex numbers, right? This would be the parameter space. I don't know what this gives me as like a nice description of the geometrically of the space. I don't know. But right, do you agree? I mean, so to know whether two normal matrices are equivalent, I just need to know what their eigenvalues are.
Yeah.
So I look at pairs, lambda and mu.
Topology of this is...
Yeah, topology is maybe not so nice because when I have repeated eigenvalues, I have some singularity.
Metric structure given by the D, U is a metric structure on a quite complicated space.
Yeah.
Even if the algebra is very simple.
I agree. Yes. Yes.
By two matrices.
Yeah. Absolutely. Yeah. I don't know how to describe it. Yeah, more simply.
Okay. Thank you so much, Bhishan.
All right.